Okay, year 13, the last section of the Astro and Cosmology book, and effectively this is the cosmology bit. So taken from where we are, the idea was we have an expanding universe, and so working out how it's moving and how quickly it's moving, you can work out how old it is. In terms of our value for h0, well, that gives us the idea of distance, therefore you're working backwards to give you an idea of time. On this picture here, this is effectively where we are now, and if we shrink this back in time, then this shrinks down and down and down to get to one central singularity, and that was around about 13.7 billion years ago. For the cosmology section, the final section of the chapter, it's so what? What does it mean? How do we know? What actually happened? And there's a big link here between this and the topics that follow on particle physics. Okay, so a little bit ahead of where we are going to go with this. So, take you to the chapter. I've renumbered it as section 4. It kind of makes more sense. I've just decided to do that this week, so we'll go with that. So, first bit is we know stuff has happened. There's a lot of research gone into this from all kinds of areas, space and other stuff. So, we know certain things, and from that we've managed to put together basically a timeline. So you need to know roughly what happens. You need to know the order of what happens, to be exact. We just need to work it through. So a bit of a time span on here. You do not need the time span, but you do need to know in depth, but you do need to know what happens first and second and third. So right at the beginning, the Big Bang itself was basically space and time, which are one aspect of the same thing. So space-time is a four-dimensional concept. Space-time begins. That's taken as our ground zero. We don't know anything before that. We can't postulate that. That unfortunately is just completely and utterly theory. It's nothing to do with physics. It would just be guessing. We have no evidence. What do we know about this time? Well, the universe was very hot and very, very dense. That's it. You can't say much else. Okay, we have lots of theories about how it happened, but we're not going to go into that. So at the beginning, right at the beginning, all we've got is energy. So we actually have no matter at this point. There are no atoms, there's no parts of atoms, there is nothing at all that could be measured in terms of mass. So no matter exists, only its other version, which is electromagnetic energy, okay, radiation. So we got photons flying around all over the place at the moment, but that is it. Okay, there's nothing else because of it. What we end up with is, because there's nothing to slow anything down, the expansion at the beginning is really rapid. So the phrase they use is inflation, okay? Inflation of the universe. And because of that idea, we get this massive rapid expansion. If you want to be really precise, it's the idea of gluon soup, as it's often called. There's nothing really to slow it down. However, about a millionth of a second, so don't forget that's a millionth of 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 a millionth. So really short time, whereas about a millionth of a second afterwards, it's already cooled. That rapid inflation causes cooling. Now, cooling is a bit of a dodgy phrase because there's nothing to cool down, but the energy spreads out, so it's much less intense. So what we get then is that energy starts to dissipate out and turn into other things. So the two groups of things that are easiest to create are known as leptons and quarks. And the two different materials, they behave in different ways. They react to some forces the same, but others are different, which we shall find out about. I should also say, and their partners, which is their antiparticles. Okay, so it's worth putting that as well in your head. Those form. How do they form? Well, because E equals mc squared. So energy is equivalent to mass. A lot of that energy is now condensing down, if you want to think of it like that, turning into mass itself. These are very small. It's worth keeping that in your head because of the whole process. So they're very small. A little bit later, again, microscopic time later, we're now only a tenth of a thousandth of a second after the Big Bang. The quarks are now literally particles of substance, so they are cooling, lose energy as the universe as a whole cools. Okay, and because of that, they start to actually fuse together. Okay, useful word, that fuse together into making bigger, more stable particles. And the two most stable particles that they form into are protons and neutrons. There are others, but they're quite unstable, so they may form into those as well, but they then tend to fall out. Okay, and another useful thing at this point, it's a bit of an extra one, because if you're looking at question marks, the main flow is it, but you might want to also consider that matter and antimatter, so that's particles and antiparticles, they annihilate, which we should go into. They basically destroy each other to produce high energy photons. Can't quite fit that. There we go. High energy photons. Okay, so we got light flying around. Now it should be pointed out that as these cool and turn into solid matter, these now have mass, and because of the conservation of energy and momentum after we've got a bit of mass, these are going slower, so the expansion is no longer in this rapid inflation stage up here. It's still expanding fairly quickly, but nowhere near as rapidly as at the beginning. Okay, so the rate of expansion is dropped. Okay, we're starting to cool right down now. We're a good 100 seconds after the Big Bang itself. At this kind of energy levels, we find that these are now stable, the protons and neutrons, as they were here, or starting to be stable. But as they cool down more, they become very stable, and they basically fuse together into particles. Okay, and what are those particles? Light, very small, light, low mass nuclei. Okay, and that's basically hydrogen up to beryllium kind of size. So, you know, quite small, quite stable, very easy to put together, but mainly hydrogen, of course. That's why we have so much of it out in space, from which we can postulate that. Now, 100 seconds, cooling, it's definitely in that flat part of the curve now, so when we have that poster that expands very rapidly and then just slows down, we're in that slow stage now. So 250,000 years afterwards, it's cooled down quite a lot, so it's worth putting again. I don't think you'd get marks for this because most people wouldn't worry about this, but it's cooled to around about 10,000 Kelvin, okay? And the crucial thing is that's low enough energy. So the reason for, low enough energy for hydrogen. Hang on, you said that already? But no, atoms are now forming. Basically, as the electrons which come into this group of leptons. So these are very small, very low mass, much less mass than the quarks, which form nuclei. These things include electrons, and they're much slower mass, so they're much faster. So you've got to cool down a lot more before they basically slow down enough for them to be captured. And at this point, basically, matter and energy decouple. In other words, you either fall into becoming matter or into energy itself. And photons can therefore, can then travel through space. You're thinking, well, it did before. No, basically at this stage, space is, shall we say, see-through. Okay, so you've got in your atoms forming, there's not all these particles, this soup of particles whizzing around all over. So now you can actually see through the gaps in between. When we get on beyond that, again, a long time afterwards, we're getting stars forming. Okay. We had early stars forming up here, to be fair, really small necessarily, but they're forming and of course dying. So what happens in that process is that the more massive elements aren't formed from this original stuff, aren't formed from this original set of particles. Okay, these are very small, helium, hydrogen, beryllium, so on. The heavier elements form by nuclear fusion when they die, the supernova. Okay. It's worth putting in supernova. Again, this is an extra bit, but and then of course today, 13.7 billion years later, or about 10 to the 12 seconds, we're at the stage where we have. So what have we got? We've got billions of galaxies. Okay, so slowing down some more, so it's not stars flying through space, they're actually starting to pull together. So you're forming galaxies, and it's worth putting each containing millions of stars. So that's the process in which the birth of the universe happens, and we can work through those. But again, basic idea is, as it cools down, as the universe and all the matter in it cools down, things move slower, and so they start to stick together into bigger pieces. Okay, so that's your kind of process. You need those stages. It will make more sense when we know what is inside what, but if you work backwards, this is what we're doing with particle accelerators. We're peeling back the layers to get nuclei, and then inside the nuclei we're trying to separate those. We're stripping off the electrons first, etc, etc. So working backwards is a bit like reversing the Big Bang. Now, if we have the right density, if this was space now, for example, as it's pulling outwards, we've still got all these particles that are now clumping and starting to form quite strong gravitational fields. So it will start to pull things towards it. And if they all start to pull each other, then what could potentially happen is we stop expanding and start shrinking again. Okay, over time. This is a possibility where we end up with our universe here. This is our first 13.7 billion years, so it's worth pointing out this is a lot longer. We might actually get pulled back together again into a big crunch, as it is technically known. Okay. Beyond that, maybe it starts again. We don't know. Again, hypotheses completely without evidence. But it all depends on, it all depends on not having grown too much. Because if things are too far apart, then there's not enough gravity to make it to pull it back and make it collapse. Now, if we just happen to have the right density, then basically we will stop expanding or slow down our expansion and then flatten off. So we end up with a static, non-moving universe. However, there is a third potential, and that is we just keep expanding, keep going on forever with nothing to slow it down. And that would seem to indicate that something is that we need to know a bit about how much density we have. Now, critical density, do we actually know what the density of the universe is? Well, again, just remind you, it's no longer on the specification, but it's basically just mass over volume. Okay, and of course, this is 4/3 pi r cubed for a spherical universe, where that is the radius of the universe. So you links into Hubble's law again. Okay, so that idea is quite sensible, but it's all on the factor that we should be able to find the mass. But we have a bit of a problem because we can't. There's an awful lot of mass that is out there that we can't see, and strange enough is known as dark mass. Not only that, we've got a bigger problem in that the universe actually seems to be expanding faster. The rate of h is changing, so the gradient of our Planck graph, our Hubble graph, is getting steeper. Now, if we look at this, we measure speeds here. Orbiting speeds of stuff, movement, should be slowing down effectively. Okay, effectively down here, but actually it's not slowing down anywhere near as much. So we're thinking there is an effect going on that may be down to dark matter that's causing a problem, or even better, dark energy. Energy. And that's interesting because we think that perhaps there's a source of energy of which we are not aware. I don't mean we don't know where the source is, but we don't know what this strange energy is. But it seems to drive the expansion of the universe. Okay, dark matter is more simple. It's stuff that we can't see. Okay, we don't emit, or it doesn't absorb radiation, so therefore it can't warm up. We can't detect it in any way other than the fact that it has mass. So we look for things like that. One classic example is from the Doppler shift on galaxies. From that we know that the mass of these galaxies must be bigger than what we think of all the stars there. So it's led to the idea of black holes in the middle of a galaxy. So if we were to look side on as a galaxy, here we go. Imagine it's a disk-type galaxy. We actually have quite a large body of mass here, and we think part of this idea of dark matter is stuff that's in there, e.g. black holes. The thing with a black hole is that we can detect them quite easily because they do emit matter, Hawking radiation. However, the other stuff we don't. We have missing mass. Okay, so dark energy I wouldn't worry too much about, apart from the fact that knowing it's there. Okay, making up around about 70%, so it's probably worth there. 70% of our unknown matter. This is around a 15%, and so put those together. 25. No, that's right. 25, 30 missing mass. Okay, so around about a quarter of it is just dark. Well, a couple of facts that we need to know. Yeah. By looking at the speed at which that is appearing and disappearing, you can measure that mass, as I say, and we can see this kind of idea comes together in that we know how the mass works, because gmm over r squared equals mv squared over r. So, yeah, v squared is proportional to 1 over r, so you can link that together. Anyway, so we have missing mass. We can find some of it, but we don't know what it is. So there's some terms you'll need to just know your way around. Might be worth mentioning in answers, might not. But we have these things called WIMPs, which are weakly interactive massive particles, big dark matter that we don't know much about, but it doesn't seem to react with stuff, doesn't seem to affect the stuff, so they don't really interact. We have machos, not machos, like nachos, but massive astrophysical compact halo objects, basically these normal everyday matter that is there, but it's massive, but it's quite hard to detect other than its effect on gravity. We have things that we're going to study a little, or mention a little bit more. Axions, which are theoretical particles, which give us something called the strong force, which holds atoms together, or atomic nuclei. And then stuff that we're going to mention quite a bit in the topic, neutrinos, like bambinos. They're neutral particles but really small, hence the breakup of the word. Here's an example of an old question, but it gives you an idea. It's just that some of the detail is no longer on the course. So here we have a question asking about the critical density. Okay, so the explanation is that is the right density between an open and a closed universe. So where it's not going to collapse in on itself and it's not going to keep expanding forever. That's that critical point, critical density between the two. Again, just be careful with your phrasing. It's the density that causes, yeah, not just it's the point. Okay, the second bit is kind of getting into this idea, so using this. However, it used to be a data book value, so we're not going to worry too much about this. Again, it's the idea of mass over volume because it's just density. However, when we get to the second part of the question, this is much more a bit like what you can expect to do. So explain open, closed and flat sections of the universe. Again, just be wary. Flat tends to just be in the middle. Okay, so we got our open, we got our closed, and our flat one curves off. Bit of a description, and then some final question like that. As I say, there's a little bit of reading on the bottom for dark energy, but that effectively is it. We can detect stuff, and again, in terms of questions, we can do some basics on it. It's all about gravity, gravitational lensing, if we can detect it, or it's hypothetical, getting into particle physics area, okay, that we look at. But for this topic, know your way around, or this part of the topic, know your way around the flowchart of the birth of the universe, as we have evidence for at the moment.